Hello, my name is Cedric Sarmiento and I will be discussing Module 1 coursework number 2 all about electromagnetic waves. Electromagnetic waves. The electromagnetic spectrum is a continuum of all electromagnetic waves arranged according to their frequencies and wavelengths. It encompasses a broad range of electromagnetic radiation from shorter wavelengths and higher frequencies, such as gamma rays and X-rays, to longer wavelengths and lower frequencies, such as radio waves. The spectrum includes familiar forms of light, like visible light, as well as various types of invisible radiation, such as microwaves, infrared radiation, and ultraviolet light. Each region of the electromagnetic spectrum has unique properties and interactions with matter, making it essential for various scientific, medical, and technological applications. Mechanical waves necessitate a medium for propagations. Maxwell's equations serve as the theoretical foundation of all electromagnetic waves back then, which travel at the speed of light. Hertz, Heinrich Hertz, validated Maxwell's prediction by generating and detecting electromagnetic waves in 1887. Electromagnetic waves can propagate through a vacuum or empty space. The waves emitted from oscillating charges can be detected over considerable distances. Electromagnetic waves transport both energy and momentum. The electromagnetic spectrum encompasses a wide range of frequencies. Speaking of frequencies, frequency is the number of times an alternating current goes through its complete cycle per second. It is also known as the international unit of measurement of frequency is Hertz, abbreviated as Hertz, Hz. We'll moving on to discuss the different frequency ranges, starting with ELF 30 to 300 Hz. Its application include AC power line frequencies as well as the low end of human hearing range. Moving on to ultra low frequencies, or also known as the voice frequencies, it is the normal range of the human voice. Although human hearing extends from 20 to 20,000 Hz, most intelligible sounds occur in this range. Moving on to VLF to 3 to 30 kHz, wherein musical instruments are used, are the main applications. It includes the higher end of the human range by up to 20,000 Hz, and many musical instruments also make sounds in this range. Moving to low frequencies, 30 to 300 kHz, wherein the main application is the uh, aeronautical and marine navigation radio navigations, used in primary communication services. Moving on to medium frequencies, where 300 to 3000 kHz, wherein the major application of frequencies in this range is AM radio broadcasting, which is 535 to 1605 kHz, and marine and aeronautical communications also take place in this range. Moving on to high frequencies, 3 to 30 MHz, wherein the main application is the shortwave broadcasting communication. These are frequencies generally known as shortwaves. All kinds of two-way radio communication take place in this range. Moving on to very high frequencies, 30 to 300 MHz, used by many services including mobile radio, marine, and aeronautical communications, FM radio broadcasting, which is 88 to 108 MHz, and television channels 2 to 13. Frequencies above 1 GHz are generally known as microwaves. Moving on to U8 ultra-high frequencies, 300 to 3000 MHz, wherein the main application is a widely used portion of the frequency spectrum including television channels 14 to 83, land mobile communications, and cellular telephones, specifically the GSM and CDMA. Moving on to super high frequencies, 3 to 30 GHz, wherein these are microwave frequencies that are widely used for satellite and radar communication. Moving on to extremely high frequencies of 30 to 300 gigahertz, it is also used in satellite communications. Only a limited amount of activity occurs in this range, which include the satellite communications as said before and some specialized radar. Moving on to radio wave propagation. In every terrestrial radio system, there are three possible modes of propagation: ground wave or surface wave propagation, sky wave propagation, and space or direct wave propagation. Let's, let's talk about ground wave propagation. Ground waves start out with the electrical field being perpendicular to the ground due to the gradient density of the Earth's atmosphere. The wave front tilts progressively. Its advantages include if given enough power, can circumvent the Earth and is relatively unaffected by atmospheric conditions. The disadvantages, however, require relatively high transmission power, require large antennas since frequency is low, ground losses vary considerably with terrain. Moving on to skywave propagation. HF radio waves are returned from the F layer of the ionosphere by a form of refraction. The highest frequency that is returned to Earth in the vertical direction is called the critical frequency. The highest frequency that returns to Earth over a given path is called the maximum usable frequency because of the general instability of the ionosphere. The optimum working frequency is 0.85 MUF is used instead. Almost all HF propagation and nighttime long-distance MF propagation is by skywave. Above 30 MHz, waves are most likely to penetrate the ionosphere and continue moving out into space. The ionosphere is the most dense during time of maximum sunlight. In general, the lower the frequency, the more easily the signal is refracted. Under the best conditions, the maximum distance of a single hop is about 2,000 miles. Moving on to space wave or direct wave propagation. The waves travel in a straight line from the transmitting antenna to receiving antenna. Space wave propagation, also called line of sight, requires a path where both antennas are visible to one another and there are no obstructions. VHF and UHF communications typically use this path. The radio horizon is greater than the optical horizon by about one-third due to refraction of the atmosphere. Reflections from a relatively smooth surface such as a body of water could result in a partial cancellation of the direct signal, a phenomenon known as fading. Also, large objects such as buildings and hills could cause multipath distortion from many refractions. As you can see here, this is uh, a diagram of the radio wave propagation. Here you can see the ground wave, and here you can see the sky wave hitting the ionosphere, as well as the direct line of sight wave, the space wave. That is all. Thank you. I have been Cedric C. Sarmiento. Have a nice day.